And after exam 2, we learn buckling and vibration. Okay. So the first structure we learn is buckling of beam structure, one column structure with two ends being pinned. And the coupling equation is here. This coupling equation is derived from the free body diagram. Each free body diagram, the moment should be balanced. This W is a deflection along the vertical direction. So this is a coupling equation. And the K is defined as P divided by EI, P squared. P is the loading. E is the critical loading we are trying to solve. E is the modulus, I is the area of the inertia. And then we assume some form for the deflection. And this displacement along the vertical direction will contain four constants, C1 until C4. Those constants will be determined by the boundary condition. And when you are using boundary condition, you can form four equations, four unknowns, right? C1 until C4. This is the first boundary condition, second one, third one, fourth one, for this beam structure. And then you have four equations. So basically, the coefficients, when you're trying to solve the coefficients until C1 until C4, you can form a 4x4 matrix. Okay? So to have a non-trivial solution, the determinant of that matrix has to be 0, and you can solve for K. K is a function of P. Basically, you're trying to solve for P, right? So if you can figure out what is K, you can figure out what is P. So the determinant of that matrix is 0. We are giving you a value for K. And you already determined the K here. So combine this equation and this equation. You can determine what is P, critical loading. So the different things, different setup will be here. Boundary conditions. Different structure will have different boundary conditions. You can form different four equations. You can form four different 4x4 matrix. And to have that determinant 0, you can get different K. This is why when you have different boundary conditions, you have different critical loading profiles. And when you finish the calculation, for this structure, you can calculate what is PCR. And then you need to check. The question may be asking what is the effective length of this structure to have buckling. You need to check this result with this definition. This is definition. This formula is definition. No matter what is the boundary condition, no matter what is the boundary condition, the critical buckling loading is defined as that way. But LEFF is unknown. You are trying to solve. When you finish your calculation this way, compare your results with that definition, you can figure out what is LEFF. In mechanics and materials, that LEFF is given to you directly. You didn't derive it. This procedure basically is to derive what is the effective length of the beam structure per buckling. So this is a first thing we learned. And the second thing we learned is when you have simultaneous buckling and torsion. This is the beam. And you not only have compressed loading, you also have torque loading applied on the column structure. And this is a typical cross-section of the beam. So in this setup, this is just an example. In this setup, the beam can be buckled in XY plane and in XZ plane, and also a torsion plane. So 3 possible buckling modes. Okay, you did one of these problems in your homework. And in this setup, you need to figure out what is critical loading for buckling to happen. You need to calculate 4 different loadings along XY plane, XZ plane, torsion plane, and then make the determinant to be 0. You can calculate another P and calculate what is the minimum buckling loading to happen. Before that, you need to finish the calculation of the sectional problem, because when you are trying to solve for that critical loading, you need to calculate PZ, PY, P alpha. This is PZ or PY. This is PZ or PY. I don't have the textbook with me. Anybody still remember? PY? Py corresponding to Iyy. Yeah, Py is corresponding to Pyy. So this is Py, this is Pz. Okay. You check your notes, make sure every notation, every equation that you're going to put in your formula sheet should be correct. So Py, Pz, P alpha, before you can use this matrix to determine what is minimum P, you need to prepare something. Right? P alpha is defined as this. A is the area of the cross-section, not the area enclosed by the cross-section. It's a realistic area of this cross-section. For example, for this one, A is the area of this one plus this one plus this one, not the area of this square. Okay? So A is the area of these three segments. You have thickness, you have length. And I0 is defined as Iyy plus Izz, and plus A y0 square, z0 square. This is area moment inertia about y-axis, area moment inertia about z-axis. A is again is area. Y0 is z0, and z0 are the distance between the centroid and the shear center. Okay, so y0, figure out what is the meaning of each of the notation. Y0 and z0 is the distance between the shear center and the center of gravity of the cross section. So when you have that prepared, you have A, you have I0, G is shear modulus, J is torsion rigidity, Young's modulus, working coefficient, L is the length of the beam, and you have everything, and then you can put all of this number into this matrix. So this is PZ0, this is PY0, this is PY, this is a sub-index of PY. You have a 3 by 3 matrix, and to make the determinant to be 0, you can calculate 3 unknowns, right? Third order equation, you can calculate 3 unknowns. So in total you have actually, if you cross out for this example, we can reduce the dimension of 3 by 3 to a 2 by 2. And then this is a reduced dimension, reduced matrix. So I did this example in class. Reduce the 3 by 3 matrix by cross out the first row and first column. Because when you look at the first row, only the first number is non-zero. Basically, you can cross out. So you can reduce the dimension to a 2 by 2. You can second order polynomial. The P is unknown. You can solve for P, and you can get some value. You can get P. One of the value of P is this much. And then you compare this value with Py, Pz, and P alpha to determine which one is the minimum. Which one is the minimum buckling loading. So this is a procedure for buckling when you have simultaneous compressive loading and torsion. This is second thing we learned. The third thing we learned is the buckling of plates. So buckling of plates, we didn't go very deep because we did this problem using essays. We didn't do hand calculation. But I introduced the gamma equation. This is the gamma equation for the buckling of columns. Right? K is related with the critical loading of P. This is one column structure. And parallel to that equation, this is the gamma equation for buckling of plates. Because a plate is a two-dimensional structure. You have x direction and y direction. So the end node, the deflection along z direction is a function of x and y simultaneously. That means each point within the plate, there's a deflection. At that point, the deflection of that point is a function of x coordinate and also y coordinate. Basically, that means this is z direction, right? This is w, x, y. Each point within the plate have a different deflection. That is why w is a function of x and y also. In column structure, w is a function of x only. So that is why in column structure, you assume w equals to c1 sine omega x, sine kx plus c2 cosine kx, something like that. It's a not function of y, but here if you assume a function for w, you have to assume that is a function of x and y both. This is assumed deflection of the plate. It's a function of x and also a function of y. This is the coefficients to be determined. And again, we use a boundary condition to determine these coefficients. The procedure is the same, only the functional form is more complicated. A two-dimensional case. In column structure, only one dimension. So basically, this is a procedure. We didn't do hand calculation in this one. So it's not going to be covered in exam. You don't have to worry about the bucking plate. Basically, for buckling, we learned only these three things. And one more thing I want to mention about buckling is in homework we did one more complicated example problem is we changed the boundary condition from a simple pinning constraint to a spring. Right? We did something like this in homework for column structure, and I put a spring here. And this is a pin. This is another pin. And I'm asking you to derive what is a critical loading for this column to be buckled. So the Gaussian equation cannot be used directly for this setup because we need to start with a free body diagram. Take one segment of the beam and draw what is the force acting on each cross section, what is the moment acting on each cross section, do the moment balance. We can derive what is the Gaussian equation. And then use the boundary condition to determine the coefficients. So this is one example we did in homework. Okay, this is what the problems we cover in buckling of beams, buckling of plates, and change the boundary condition. So and then we learn vibration analysis. So vibration analysis is different from all of the structural analysis we learned before. All of the things we learned before is starting with equilibrium. Total force is zero, total moment is zero. All of the equations we used, even for the buckling of beams, we start with the free body diagram, the equilibrium of each segment. But for dynamics, for vibration, we have inertial term to worry. So it's not just simple total force is zero. Total force should be equal to m times the acceleration of the system. We have inertial term. To construct the Gaussian equation for vibration, we start with the construction of the so-called Lagrangian energy function. L, Lagrangian energy function. So it's determined as kinetic energy minus the potential energy of the system. For a spring mass system, the kinetic energy is very easy to determine. Each mass has a different velocity. Each mass has a different degree of freedom, displacement x1, x2. And if you take a time derivative, you will get velocity of each mass. And put them together, you get kinetic energy. And potential energy for this spring mass system is associated with the springs only. The two springs. Each spring is elongated. You just use 1/2 Ku squared. This is the definition for the potential energy of the spring, right? So the first spring, this is the elongation, Ku squared divided by 2. And for the second spring, this is the elongation, x2 minus x1, because they are elongated in the same direction. So the total elongation of the second spring will be the difference between these two ends. And then you can form the Lagrangian function of the whole system. And then according to these two equations is something like principle. It is so-called energy principle. Energy principle. Extremize the energy of the system. Extremize the Lagrangian of the system. We will give you this equation. You have 2 degree freedom. L is in terms of x1 and x2. So you will get 2 equations using this energy principle. Do the derivative term by term. This one, you can from one equation, and this is the first equation. This is the second equation. If you follow these 2 equations, you can derive a matrix form m x1 double dot x2 double dot plus k x1 x2 equal to 0 if we do not apply any external force. M is a mass matrix, 2 by 2 mass matrix. K is a stiffness matrix. Because you have two equations, you can rewrite those two equations in a matrix form, and you form the mass matrix and stiffness matrix. So for spring mass system, it's quite straightforward to construct the L. But for continuous system, we did some derivation. For bar or beam, how we are going to form the mass matrix and the stiffness matrix. This is a one elastic bar. Density, cross-section area, Young's modulus. And this is a mass matrix we should have for this elastic bar. And because for bar elements, you only have two joints. Right? For each joint, you only have 1 degree of freedom, because bar is only allowed to deform along the actual deformation. It's not allowed to be bended, different from beam structure. So 1 degree freedom along this direction, another degree freedom along that direction. That means you need to construct a 2 by 2 matrix for mass matrix, and also 2 by 2 matrix for stiffness matrix. Basically, the end node is ui double dot uj double dot plus this is m, this is k, ui uj. Parallel to the spring mass. In the spring mass system, there are two unknowns x1 and x2. Right now, you just change that spring to a bar. So you will have ui uj, which is two unknowns. And that means the dimension of m and k has to be 2 by 2 for this bar element. If this is the definition, that means this n is 2 by 1, and this n is 1 by 2. This is a transpose of n. So in stiffness matrix method, we define n already. A is so-called shape function. Shape function is also interpolation function. Basically, that means this is I, this is j. If the displacement here is ui, the displacement here is uj. This is not direction, this is a magnitude. Okay, ui that much, uj this much. And what is the displacement here? So this function will tell you what is the, this is x direction. 1 minus L x. So you tell me what is the value of x, I will use this function to tell you what is the displacement here. This is called interpolation. You have the displacement on the two ends. I want to figure out what is the displacement at one point in between. I do not have to calculate it. I just want to do the interpolation using a defined function. You can define a nonlinear function, a high-order polynomial to do the interpolation, but this is simplest one. You can just use linear interpolation, so-called linear interpolation, first-order interpolation. Okay? So this n is 2 by 1. And then you use 2 by 1, you can form a 2 by 2 mass matrix. This mass matrix escape the duration. This is a mass matrix for one bar element. I didn't do any assumption for this duration. So this is universal. You can put this formula in your formula sheet. But different bar elements will have different A and M. That one you have to be very careful, right? Different bar elements use different density. So this is a mass matrix for one bar element. If you have multiple bar elements, you can form multiple mass matrix, M1, M2. And then do the summary. You form the global mass matrix for the whole structure. And next step is what is K, right? Because this is an equation that you're going to need to solve for the vibration frequency. This is a summary of this two mass matrix. And K is a stiffness matrix we learned in stiffness matrix method. Just 2 by 2 equations, EA over L, and this one is universal, but for each bar element, you may have different modulus, area, and length. So for two different members, you have two different K. Again, do the assembly. You can form a 3 by 3 matrix for this example. For this example, why you have a 3 by 3 matrix? Because you will have 3 joints, 2 members. Right? The total degree of freedom for this structure is 3. Each joint have 1 degree of freedom along the axial deformation. So this is how we are going to form the global M and global K. And then we apply the boundary condition. We apply the boundary. This is K. This is K. This is M. This one is M. This is K. I have this example in your lecture notes. You can go back to check. So for this two bar member structure, I do the assembly from the global K, from the global M, and then apply the boundary condition. Cross out the fourth row and fourth column because the fourth joint, I put a fixed end there. So this dimension of A can be reduced to 2 by 2. And then you have K prime at here, M prime at here. So this is a reduced K, this is a reduced M. And then you can solve this frequency by hand. 2 by 2 matrix, the determinant of this A prime is 0. You will have a 2 by 2 matrix, 2 unknown, just one unknown, omega, but you will have 2 solutions, right? The determinant is A matrix is 0. That means this is 0. So this 2 by 2, this is a 2 by 2 matrix minus another 2 by 2 matrix. Coefficient is in terms of omega, so you have a 2 by 2 matrix in terms of omega. You can get 2 unknown, you can get 2 solutions for omega. That is so-called natural frequency. Because for this structure, you only have 2 degree freedom. The second joint and third joint, you only have 2 natural frequencies. So how many natural frequencies you will have will be determined by how many degree freedom you will have in the structure. So that is why in your project, everybody is using a different mesh. The natural frequency for each of you will be different from the others because everybody is using a different mesh. Just imagine I discretize this structure into 10 bar elements. You will get 10 different frequencies. And the difference between those 10 different frequencies may be not that huge because you just put more mesh into the structure. But number will be different. So everybody should be getting a different frequency. If you get exactly the same frequency with the other one, that means you just copy its mesh. So that will be not cheap. Okay? Everyone should be slightly different in natural frequency at least, because you will never guarantee you are using exactly the same mesh with other students. So that is why also I do not have a general solution for this one, for this project. Everybody will get a different number, but shape will be very similar. The vibration shape will be very similar. Okay? So this is a hand calculation about natural frequency, and also according to natural frequency, you can determine what is so-called eigenmodes. Just put when you get what is omega 1, omega 2, just substitute the values omega 1 and omega 2 back into this matrix and solve for the relation between U2 and U3. For this one, you will have U2 and U3. So for the relation between U2 and U3, that is so-called eigenmodes. So this is a bar element, and we also learn something about beam element. Beam elements, the procedure is exactly the same as a bar element. The only difference is we need to change the n. Let's go back to look at the formulation. This is the derivation for the bar element. Each bar, 2 joints. Each joint, 1 degree freedom. But if you are looking at beam element, you will have deflection, rotation. Deflection, rotation. So for each joint, you will have 2 degree freedom. And That means in total you will have 4 degree of freedom. One beam element, 4 degree of freedom. So that means the mass matrix, the equation you are going to solve is M Ui Vi, because deflection along that Vi theta I Vj theta j. This is the Gaussian equation for beam element plus K Vi theta I Vj theta j equal to external force. So this is the Gaussian equation for beam element, 4 unknowns. And as a consequence, the mass matrix, the stiffness matrix should be 4 by 4, right? So that is, this one is for beam. No, that is for bar, only 2 unknowns. Coefficients should be 2 by 2. Now you convert that element to a beam element, this is 4 by 1. Definitely you need a 4 by 4 matrix. So when you come to this universal formula for M, that means you need to have 4 by 1 here and 1 by 4 here. And then you change the interpolation function. In answers, you choose a so-called cubic polynomial interpolation. That is telling you which n you are using for beam element. I also give you some formula for n. You will have n1, n2, n3 until 4. And you have 4 different n. If you use that 4 different shape function, you can construct M matrix for beam element. Okay? So stiffness matrix is the same as what I have learned in stiffness matrix method for beam element. That is also a 4 by 4 matrix. So the only difference for vibration analysis from the stiffness matrix analysis is we need to construct M. The M, universal tree. This formula is universal tree. We always use this function. But you need to tell me what is interpolation. How you are going to inflate the displacement within the element. That is the element. How you are going to tell me what is the displacement here if I can solve for the displacement of the two points. That is flexible. That is flexible. Different people with different software, even answers, many different options. You choose different information function. And then you will have different M matrix. But it will be slightly different. If you use different N, you solve for the frequency, you will see the difference. That is because the reason is because you are using different N. M matrix will be different. Okay? So this is a vibration analysis of spring mass, bar, and beam. We didn't do plate because plate for hand calculation is not easy. And the procedure is the same. For plate, the degree of freedom here, this column maybe become more than 4, right? If you have 3 joints for a triangle, that is one piece of plate. For example, this is one plate, IJK. Okay, this is one piece of the plate. And this is one element. In total, you have 6 degree of freedom. Each joint have 2 degree of freedom. So this one becomes 6 by 1, and then you are going to need to form a 6 by 6 M matrix. So this is a procedure. This is basically the beauty of the finite element. If you know how to do truss, you will know how to do beam, plate, and even solid. The procedure is the same. You form K, you form M, and then solve for that mu dot dot plus Q equals to F. Solve for that equation. So this is what we have learned for vibration. And then next thing we learned is procedure for the modal analysis. We didn't go very deep for this method because the hand calculation takes more than 1 hour to finish one solution. Even for this one, you need to finish the calculation of eigenfrequency first, and then convert those equations into the normal coordinate, and then solve those equations in normal coordinate, and then transfer the solution back to the Cartesian coordinate. So there's a graduate level course in, I don't know in our department, at least in mechanical engineering, we have a course called vibration, or introduction to vibration. The whole semester we are dealing with this. How to solve this mu dot dot plus ku equals to F. Okay? So the idea is construct an equation of motion. When you finish the construction of motion, you will see, okay, these 2 equations are in terms of x1 and x2 simultaneously. if you just want to solve this equation, x1 and x2, both of the unknowns are there. It's almost impossible to solve it. That is why model analysis is useful. Motivation is transform this unknown from Cartesian coordinate to normal coordinate, and then decouple those two unknowns. Each equation, after you do the transformation, will contain only one unknown. That is a good thing about model analysis. The procedure is the first step, calculate the frequency and choose a distinct frequency, natural frequency, calculate the natural frequency and choose the different ones. If the same frequency will give the same eigenvector, that is what we are going to use that eigenvector to do the coordinate transformation. So we need to choose different natural frequency to have different eigenvector. And then you just put those eigenfrequency in ascending order, and then calculate the eigenmodes, normalize that. And the most important step in model analysis is to form this phi matrix. When you finish the calculation, of the eigenmodes, you will have how many degree freedom you will have, and then you will have how many eigenfrequencies. Each column is one eigenmode or eigenvector. Okay, 1, 2, until n. So you have multiple eigenvectors. Put them together in a matrix. Why this matrix? Matrix is going to be very useful because using this matrix, we can transform the coordinates from the Cartesian coordinate to normal coordinate. And use this matrix, we can transform all of the mass matrix, stiffness matrix, even the force matrix from the Cartesian coordinate to the normal coordinate. And we are going to solve that equation in the normal coordinate. Because in normal coordinate, each equation only contains one unknown. So when you form phi matrix, do the transformation and rewrite the equation of motion into skip this one. So maybe I use this example to show you how to do the transformation. This is example I used in class. Right? 2 degree of freedom, 2 unknowns, x1, x2. This is a forced vibration. You apply an external force on each mass. It's not easy to solve for x1, x2 directly if you just use the equation motion. This is a 2 equation motion. This is a 2 equation motion in x coordinate. If you look at that 2 equations very closely, you will see each equation is in terms of x1 and x2 simultaneously. So we are going to transform this equation motion into normal coordinate. The first step is to figure out what is the frequency, natural frequency. This is same thing as what we have done in calculating the natural frequency omega 1, omega 2. Determinant of that matrix is 0. And when you finish the calculation eigenfrequency, you substitute this eigenfrequency back into that matrix. You can solve for the eigenvector. When you substitute omega 1 into that matrix, this omega becomes omega 1, and you can figure out what is the relation between x1 bar, x2 bar. Those two values are the vibration magnitude. So this is the first so-called eigenmodes corresponding to the first eigenfrequency. If you use omega 2 into that matrix, you can get another relationship, another ratio between xy bar and x2 bar. This is so-called second eigenmode, another eigenvector. When you have 2 eigenvectors, you can form the total phi matrix. The first column is the first eigenvector, second column is second eigenvector. We are going to form a 2 by 2 matrix for phi. We are going to use this phi matrix to transform everything in Cartesian coordinate to normal coordinate, m, k, and f. After you do the transformation, you will see each equation will contain only one unknown. This is the procedure how we transform M matrix. M is a mass matrix you form in Cartesian coordinate. Phi is a matrix you form through the assembly of the eigenmodes. 2 by 2 times 2 by 2 times another 2 by 2. 3 2 by 2 matrix. And you finish the calculation, you get another 2 by 2 matrix. This is so-called diagonalized mass matrix in normal coordinate. Okay. The good thing about this M matrix is you have non-zero on the non-diagonal term. Okay. Actually, initially this case is very special because you only have non-zero on the diagonal term. This is spring mass for truss or beam. Everything if you recall the mass matrix for M for bar elements, you have non-zero value here, not zero. So this is zero because this is spring mass. It's very special. So this is how we transform the mass matrix. We can do the same thing for K matrix. This K is a stiffness matrix in Cartesian coordinate. This is an eigenvector matrix transpose. And when you look at the original K, you have non-zero here and non-zero here. That is why those two unknowns will be coupled, because you have non-zero on the non-diagonal term. If you put this transformation, you can get 0, 0 here. You only have non-zero number along the diagonal term. So you transform M, K, and even F. If you have external force, you can transform F. So this is F. How we transform F? This is external force in Cartesian coordinate. This is an eigenvector matrix in normal coordinate. This eigenvector matrix will form from the eigenfrequency calculation. And then when you finish the transform, you can form the equation of motion in normal coordinate. This is the equation of motion in normal coordinate. Q is a normal coordinate. Everything is in Q coordinate right now. It's not in X. MD Q double dot. Originally it's MX double dot. Right? KX becomes KDQ. F becomes FD because everything is diagonalized already. So if you substitute MD and KD into this equation, this is MD, this is KD, and this is FD. 2 by 2 matrix, two unknowns, Q1, Q2. If you expand it, you will see each equation will contain only one unknown. The first one will contain Q1, the second one Q2. I expanded. This is what I showed last time. If you expand the 2 by 2 matrix, the first equation will be in terms of Q1 only. So mathematically, it's much easier to solve for Q1. When you finish the calculation, what is Q1, and then transpose Q back to X coordinate, you can get what is X in the Cartesian coordinate. This is the procedure. Even you go to graduate school to learn what is the course of vibration, the whole semester you are going to deal with this. Much more complicated system, much more complicated boundary conditions. But the procedure will never change in a second. So we didn't learn much other than exam 2. Buckling, vibration, buckling of columns, buckling of compressive loading and torsion simultaneously, and buckling of plates. And then vibration. Spring mass vibration, truss vibration, beam. We did. But we did one problem in axis. So natural frequency of frame structure, we did one of that. We did a mechanical calculation. And then mode analysis. Mode analysis basically is you need to know what is the procedure, how we are going to transform the coordinates in Cartesian coordinate to normal coordinate. How we are going to diagonalize M and K, because this will give you convenience to solve what is the vibration displacement. Okay, not much. So I'm going to update with you which classroom we should take for the exam. So please check the announcements on the EP system, and also I'm going to send an email to you guys. Hopefully we can stick to this classroom. There's no time conflicting with event.
Excited to organize again.